This is problem number 7 of the QHack 2023 Quantum Coding Challenges, and it's entitled Optimize This. So what we're being asked to do in this problem is to construct a basic circuit that would help us understand the basics of quantum machine learning. So the idea here is that we're going to have two main blocks. Here, one of them is denoted embed. And what we're going to do here is we're going to pass to this block some classical data. And we're going to embed that data in the form of the amplitudes, the probability amplitudes of a quantum state. And then we're going to construct another block called basic entangler layers that we're going to train. So this is going to be a circuit that is going to have some parameters. Typically, these are in the form of rotation angles in either RY, RX, or RZ gates that we're going to be modifying to meet some criteria. And that criteria is basically our cost function, which is measuring the expectation value of some observable. And what we're being asked to use as the observable here is the sum of the poly z operators of the output. So if we have n qubits, our observable will be the sum of the poly z on qubit 0, poly z on qubit 1, all the way to poly z on qubit n minus 1, and then take the expectation value of that. And then we're going to optimize the parameters of this basic entangler layer or layers by using gradient descent to minimize that expectation value. So let's go step by step and describe each of these blocks. So starting with this amplitude embedding, what we have here is a block that takes in some classical data. So we're going to represent that in the form of a list or an array where we have different data points. And the way this block works is once we pass that data, it generates a circuit that at the output, if your inputs are all 0 states on each of the qubits, the output is going to be the state psi, represented by the sum from I equal to 1 to n of all the basis states with a probability amplitude given by this equation here, where for n smaller or equal to m, each of these probability amplitudes is basically each of the classical data points divided by some normalization factor a in order to guarantee that the norm square of this probability amplitudes sums up to 1. And for n larger than m, we just have this c padding constant that we add to the rest of the data. And typically we can just set that c equal to 0. So if this is not clear, let's maybe look at an example, right? So let's say our classical data that we want to embed is just a data point 1, 2, and 3. And since we have 3 data points, we're going to need at least 2 qubits. But with 2 qubits, we can represent up to 2 to the 2 states, so a total of 4 states. So we need some padding constant, and here we're going to use that padding constant equal to 0 for that last state. So our unnormalized state will be the amplitude 1 times state 0, 0, the amplitude 2 times 0, 1, the amplitude 3 times 1, 0. And that's all our classical data, and then we just have this padding constant of 0 multiplying state 1, 1. So then we can just ignore this. Now, if we perform the normalization, we need to find this a that will guarantee that all those probability amplitudes will sum up to 1 once we take the norm squared of each one of them. And that just gives us this value of 3.74. So the normalized final state vector will be given down here. So basically, this is how we encode this classical data with data points 1, 2, 3 in the form of a state vector using amplitude embedding. Now, when it comes to basic entangler layers block in pennylane, the way that is constructed is in the form of a series of rotation gates. I denote them here with R sub I because we can specify if we want that I to be an X rotation, a Y rotation, or a Z rotation. And it basically consists of two dimensions. So one is the number of qubits that we want, and another one is the number of repetitions of this block. And we have just basically single qubit rotation gates and then entangling with CNOT gates from one qubit to the next one all the way down, and then an entangling gate, a CNOT gate, from the last qubit back to the first qubit. And then that's just repeated L times, where L is the number of layers we want. So basically, the way we need to pass the data into this block is in the form of a matrix where one dimension will be the number of qubits we have and the other dimension the number of layers we want. And that matrix will encode first the initial values for these parameters that we want to train, and then as they get trained, they will change until we reach the final value once we perform gradient descent. So let's take a look and see how we implement this in pennylane. So as always, we import pennylane as QML and then NumPy. And the first thing we're going to do is just select some data that we want to embed, right? And this is unnormalized, and in the coding challenge, we're giving some extra lines of code to normalize this, but I want to show you how we can just basically tell the amplitude embedding block to do this for us so we don't have to normalize it ourselves. So let's create that list with data, and then as always define our device. And here we're going to use 3 qubits for this example. Now let's define our circuit, which we're going to call cost, because the output of that circuit is basically the cost function that we want to minimize using gradient descent. And we're going to pass this parameter weights, which are the ones we want to train. So basically, these are going to be the rotation angles of those rotation gates inside the basic entangler layers block. And then we're going to pass the data directly. And then we're going to do QML, amplitude embedding. And we're going to pass here features as the data that we want to embed. And then wires equals range 3, because in this particular example, we're only using 3 qubits. And this is what I wanted to show you, that here, even though we're passing unnormalized data, this amplitude embedding operation has this normalize parameter that if we set to true, then it will normalize this for us, and it will generate the correct state vector already with the right probability amplitudes. So then we're going to do QML basic entangler layers, and then we're going to pass weights equal to weights, which are the parameters we want to train, and then wires equals range 3, again, because we only have 3 qubits. Now, here in this problem, what we're being asked to return is the expectation value of the sum of the poly Z observables on each of the qubits. So in order to do this, what we've seen before is that if we want to return, for example, the expectation value of each of these poly Z observables, we could do it in the form of a list, right? So we were doing QML, xval, and then we were doing let's say poly Z of wire, and then we were using list comprehension, right? So for wire in range, in this case 3, and this will give us the expectation value for each individual poly Z observable. But this is not what we want, right? What we want is the expectation value of the sum of the 3 observables, in this case 3 because there's 3 qubits. So a way we can do this is that if we look at just this list of poly Z observables, we have them separate. Well, pennylane has this function QML sum that gives us the sum of the observables we pass to it, or the operators we pass to it. Now, the only issue here is that this QML sum takes each of these operators independently. It does not take them in the form of a list. So if I try to execute this, it's going to give me an error. So in order to pass them separately, all we need to do is unpack that list. So we can do this with the unpacking operator in Python. And then, as you can see here, we will get the sum of the poly Z on qubit 0, poly Z on qubit 1, poly Z on qubit 2. So with this, we can just then here return the correct expectation value, right? Which would be the expectation value of this sum of operators, right? So once we have defined our function, we're given 2 lines of code, and I'll explain what they do. So here, this first line, what it's doing is finding the correct shape to pass the weights to this basic entangler layers. So as I described before, these weights must be passed in the form of a matrix where one dimension represents the number of qubits we have, and the second dimension the number of layers, right? So that we're passing the right angles to the right gates in this basic entangler layer circuit. So all this is doing is just extracting the shape of that matrix if we're going to use 2 layers, and then it's taking the weights in the form of just a list and reshaping them into that matrix. So if I print here those weights, you can see that this array or this list gets turned into the right matrix that we're going to pass to this circuit. All right, so then the last thing we're going to do is just perform gradient descent to train the circuit and find the final weights. Now, luckily, pennylane has an easy way to do this. So all we need to use is this QML gradient descent optimizer function, and we're told to use a step size of 0.01. And to now train the circuit, we're asked to only do it for 3 steps. Ideally, we will do it for more than 3 steps to find the values of the weights where this converges to a minimum. But I guess for the grader, they're asking us just to use 3 steps here. So then all we do is just assign to weights the updated version of that. So all we need to do is use this object OPT, which is of this type gradient descent optimizer, and we use this step function in here, and then pass our cost function circuit, which we call cost, and then the weights, the current weights we have, so that we perform gradient descent and update those weights accordingly. And then if we go here and print that cost function after we have updated the weights, we get a value of 0.066, which if we go here and see what we're given as a test case input, which was the same array of data I used in this example, we get this is the cost we're getting after 3 steps of performing the gradient descent process. So I hope this is helpful. Let me know if you have any questions.